The first of this afternoon's session. My name is Mike Malin, and I'm from the University of Newcastle in Australia. So we've got two talks which are very related to each other, both on wave scattering in the marginal ice zone. And the first is the viscoelastic model for wave propagation in the marginal ice zone, given by Sukun Cheng.
Oh, do you know how to start it?
I think it's on. Yeah.
This is
Is there a red light?
So, good afternoon, everyone. Thanks for giving me this chance to talk here. And my talk is about viscoelastic model for wave propagating in the marginal ice zone. This work is sponsored by ONR, and a part of my talk will be related to the Sept project. For people not familiar with project, this one is about how wave project in the Arctic Ocean. This talk will about wave-ice interaction. And we all know the ocean wave affect ice by breaking it and pushes them and drift the ice around the ocean waves. And on the other hand, the sea ice will affect ocean waves. As the wave propagating into ice cover, it will be reflected, transmitted, and scattered. And also the wavelengths will be changed. As we saw in the inner field, there is only long waves survived. Also amplitude decay as in the wave directions. And in this talk, we only talk about the second topics. If you look at the topic picture, there are different types of ice of different size from the in ice field to open water. If you look closer, there's very big, thick ice people can work on, do experiments, and very smaller size from millimeter to tens of meter pancake ice, which is most popular one now in the Arctic. And the gray size is close to open water. Actually, it's a cluster of ice crystal at the beginning of ice first appeared. So we think this different type of ice will affect wave in different way. Here I list three very important models by assuming the ice by different material. First is mass loading model. It assumes ice are just ice mass point floating on water, and there's no interaction between those points. And another one is thin elastic model. This one, ice layer is assumed the whole continuous homogeneous layer and the same thickness, but most important is pure elastic. So it can storage energy and have wave propagating longer, and wavelengths will become longer. And the third one is assume ice layer is a viscous one. People want to use this model to explain how and why the wave is decay in the direction of wave propagation. But in the real field, we usually see its ice not pure type of pancake or elastic ice sheet. Usually they are mixture together. And as recent years observations, multi-ice decrease, this type of ice is became more popular in the Arctic now. And inspired from the elastic and viscous model, we think this mixture ice may have both elastic property to storage energy and the viscosity property to dampen energy. So we introduced the viscoelastic model. And it's again following the same assumption, similar assumption. It assumes the ice layer is a pure viscous, homogeneous, same thickness, and this scratch shows how the material responds by apply under the force. Is a spring and dashpot in the parallel pattern. Compare this model with previous model. One advantage is this if you tune in the parameters, the elasticity and the viscosity and thickness, you can reduce the previous one in most of the time. And if we will look closer about the viscous layer model and this one, we just replace the, or just instead of the pure viscous parameter, introduce an elastic parameter. Following the same mathematical form, we can get the differentiation of this model. And this is quite long. I'm going to not talk about this one. Only the parameter side. Now it's a complex wave number. The real part is wave number that's related to wavelength, and imaginary part is attenuation rate. And it's related to these parameters: frequency, ice thickness, elasticity, viscosity, and density of water and ice, thickness of depth of water. Usually in the study, density and thickness are not, the density and the water depth are usually constant, so we're mainly concerned this fall. This disproportionation will solve infinite number of roots. A good way to show these roots is draw the counter plot, as here is the wave number against attenuation. And this root will be shown as those black dots, and this figure on the left is the zoom in of this region on the right. And first, those roots along y-axis, we call it evanescent mode because it's only survive as the SIH next to the open water. It's not our interest. We interest the wave that can propagate long time from the SIH. So they are the one called traveling mode. And the roots KR and KI related to the modes because the wave we saw in the real field, we believe is a superposition of different modes. And that's why these roots are important. If we specific our interest in is the roots is the wave propagating from left to right, and with positive damping, we need to look about the first quadrant. And because those roots are damped so fast from the ice edge, this again is not important after a long distance. We only need concern a small region. So we zoom in the area, and we found there are 5 roots. Compared with previous models, there's a lot of roots, and we should focus on 1 or 2 which we should pay more attention. Which one is important? This question is first answered by the authors who proposed this model. By reviewing previous models, they summarize there are 2 criteria to choose the roots. First is the roots related to modes that is close to open water. Another is the mode can stamp lowest attenuation. This is very trivial, and after we play several years, we find these 2 criteria are not always in agreement. Then we have a dilemma to choose. For example, if we use this set of parameters and draw the 2 roots as the blue and black one, this is wave number, this is attenuation, and add the open water for reference. If we use first criterion, is to choose one close to open water, then we get the dominant mode as marked as the red square. And if we use another criterion, we get a different choice at high frequency part. So this makes us looking for more reason why there is a disagreement. And recent work, we go back to the physical meaning of these roots. And the conclusion we get is this root 1 and root 2 are related to a gravity wave and a pressure wave. The root 3 is related to a shear wave. Actually, they are solid mechanics atoms. And this one doesn't contain energy in this model, so this is not important. And number 4 and 5, the really lamp wave, they damping too fast compared to 1 and 2, so we don't consider about them. And this answers the question why we compare just root 1 and root 2 in last slide. And now we are more clear now. We are looking for is a gravity wave. And the pressure wave that actually moving forth and back is a longitudinal wave. We can't measure in the field, so we should choose the other one, not pressure wave. So we get the new criterion is to choose with the wave number farther from this pressure wave. Let's see an example. For this set of parameters, just we change the g value half of the previous one, and we use the previous two criterion to choose. We find both of them we can get, they are in agreement, and get black one. If we choose the new criterion, and we put the pressure wave and the thin elastic model solve the flexural gravity wave, which is the green one, and we got a new result. And this one seems more reliable because it agrees with the thin elastic model better. So now we are more confident to use this mode in application. And now this viscoelastic model has been tested in the WaveWatch 3, which is the ocean wave model as IC3. We all know the CIS part contains the conservative like scattering and the non-conservative dissipation. And this model only serves the dissipation part, as the group velocity is related to wave number, attenuation rate, and F is wave spectrum. So before apply this model, we need to know first is what's the elasticity and the viscosity. Because these two parameters is imagining the equivalent of viscoelastic layer. We can't measure it in ice. So we think we can calibrate use the field data. And the objective is to get the measured wave number and measured attenuation. So next part, I will show a work in calibration using field data. And this campaign is done on the Beaufort Chukchi Sea, just north about Alaska, and during this time. And we see different ice type, very big one, smaller one, pancake, small pancake, and actually open water during the time about 42 days of this campaign. This has a big role, this is a big campaign including the Sea State project. And they have tons of measurements from base and buoy, ship, and waters. This is also buoy. Remember, we need is wave number and attenuation rate. So we're first looking for the attenuation rate. And we mainly use two types of buoys. And this is how they working on ice. The ship just drops the buoy and go away. And after several days or hours, the ship come back, pick up the buoy. What we do is we pick up two buoys working at the same time, and actually it's 30 minutes. And we get the wave direction based power spectral density, and use this one to get attenuation rate. But we do not directly relate this measured attenuation to the models. We put it through the energy balance equation, and made a little simplification now is to delay the time derivative term, because we assume is all the data we use is 30 minutes average. I think this is not important one. And group velocity is take out, assuming the wave speed doesn't change much during this time. And it shows group velocity and this ice source turn are related to the CIS model. And this alpha is just related to the derivative of energy we just get from previous slide. And there is another source term. We introduced three important sources when studied open ocean wave. They are the wind input, which is as wind blows the surface is input energy to the wave, and the wave dissipation is like wave breaking at the surface, and another one is nonlinear wave-wave interaction. It's measuring the energy transfer between different waves in the ocean. So this is a marine data. It's a marine radar picture. As the blue line is the shape. This is during 30 minutes, and we have one arrow marks one buoy, and there's another buoy. So from this region we studied is not fully covered by ice, and those water part is also important because during these days there is a big storm. It's about 5-meter wave height, and that's why those southern open water are also important. And we scale them by the ice concentration, the same way as used in WaveWatch 3. So finally, we get a relation between the measured attenuation rate and the theory. And we also consider the weight factor is considered as according to the power spectrum, because we want to fit over the whole frequencies, and most energy are conserved between 0.1 to 0.2 Hertz. To fit the high frequency part, we need this one. In the previous one, we have the wind turn and other wave turn, so we need some sources from remote sensing. And this is contains more time the other part, because I need to organize all those source data from different remote sensing source, and the one get on the ship by man and by instrument, and finally we choose one the working best, the remote sensing, which can get best ice thickness and concentration along the ship track to compare with the measurement on ship. And we get M32 for the ice concentration, which is Japan's radar satellite, and the thickness from SMOS. Sorry, we didn't use CIS because the data we get is very coarse than the other two. And the similar we do for the wave source turn, for the wind source turn, we need wind speed, and we get is we use NavGen compare with the speed measurements installed on the ship. It's get good agreement. So we think we can use this measurement to apply to the field of buoys. Next is about wave numbers. We have two measurements about wave numbers. The best measured is about marine radar, which is installed on the ship. And as you see, there's some tissue. You can see the wave height. And this small white point is the ship. So it can cover the area about 8 kilometers, 4 kilometers around the ship area. But the problem is only can measure at frequency up to 0.4. If we want to know more, we need this another method based on the shape. It's correlating the slope of the buoy that is drifting on the water, so as slope, and correlated this with the wave height, the heave motion, and we can get this one. Unfortunately, this data is only applied to one wave experiment, and when we collect data, we find we have many cases of attenuation from experiments 3, 6, and 7, and only experiment 3 have wave number data. And this only applies to one type of buoy. So conclusion is that there's no enough wave number data, but we have a lot of alpha. So we made a compromise. The second fitting factor, we use the open water wave number, because when we look closer about this, And this wave number ratio with respect to open water is nearly 1 for marine radar, and this one is a little bit higher, but these techniques we think is not as reliable as this. So it's still somehow is using wave number is reasonable. Except in another 2 experiments, we have no measurement of wave number. If we use a measurement from the wave experiment 3, it's not better than use just wave number from theory. So we optimized each the alpha curve we got in the last slide, and through this 2 objective function, using the genetic algorithm, we get some scattered points, and each one corresponding to a alpha attenuation. This for experiments 3, 6, and 7. They have different clusters, and we use binomial distribution to describe them as the black one and red one. You don't need to care about the black ones, you just get rid of the outlier. And why there are 2 clusters, that's quite interesting. And when we look at the picture, we find on experiments 3 and 7, there is takes a long time, so they encounter different ice type. And 6 only take about 1 day, and the ice is very stable during that day. If we summarize this G and new location here and compare with the ice concentration and thickness, we find 7 is stronger ice than 3. And that is agreeing with our expectation that stronger ice will have larger G value than the weak ice. And there is an interesting thing during wave experiment 3 that when the wave is very high, about 5 meters, from forecast, the scientists think that day the wave will push the ice together and make them locked together. And those locked pancake ice will prevent wave penetrate further. So they put a lot of instruments in that day. And the ship go away. After half day, they come back. There's no ice. The reason is there's the warm water layer below the surface, about 20 meters, because the very strong storm that can drag the warm layer up and melt all this ice. So what they got is not very good, very unexpected result. I'll go back to this. And then we validated the data. We validated this with experiment 3 about we use this calibrate G and new value. The G is very low, about 10 to minus 4. And we find for this model, for 10 to minus 8 to 1, there's no much difference. So we use G 10 to minus 4 as calibrate. And we get G a new value from 1 to 100. So we pick 5 of this new value and put it into wave 3 to do handcast. And compared with this data, this figure shows is the wave experiment 3, how the ice, the white part is ice, and is this AVAC is this one. It's mountain and water, and we compare the wave height and the peak wave period. As this black dot measurement is within the prediction part, prediction about using wave watch 3. And you can see it's agree with the yellow one, which is nu equal to 10, reasonable, except this is lower. And the nu equal to 1 is the center of this calibrated new value. So we think this calibration is reasonable now. So as a summary, I introduced the viscoelastic model and talk about their infinite roots and how these roots related to the wave modes and how to choose the wave mode to study in the future. And I also talk about calibration using field data. And we think this method will work. So in the future, we want to use this method to do more field calibration. As this picture shows, there are different types of eyes. And for this calibration, just a talk is near the marginal eye stone, very close to the open water, because the shape is not edge broker. It can't get inside. And also the drifting buoy, if they inside, I think they will frozen. For example, in this campaign, some of buoy is they have camera on it, and they have speed limiter. They all frozen during sometimes, and buoy lost. So in the future, we rely on more reliable instruments. And now, when we run this in W3, the WaveWatch 3, we use a very core method. We set the whole area of eyes using the same type of J and nu, same value of J and nu. And the value chosen empirically. And we know for different eyes types, they should have different J nu value. So if we can get calibration for different eyes types, in the future, when we apply this model to WaveWatch 3, we can make a more finer grade and identify which G nu value for which eyes type, and hope that can make this model works better. Thank you.
Thanks a lot, Sukun, and I'm going to be giving the time as well. So, some questions,
Just a couple of questions. Firstly, the addition of distance from the pressure mode, which is quite clever, but of course, when you run with different G and nu, the modes will move around in the complex plane. And are you still going to run into problems where the modes get very close together and you won't be able to distinguish between them?
Yes, this is a big problem we want to work next. It's called mode swap between these two modes, and this first find when I think it's the Rempel study the wave propagating into the polar material, and they do have very close time. We can't identify which one is which one. And at that time, if we look at the orbital about the parcel, both of them are not pressure waves. So in the future, maybe we want to keep both of them for WaveWatch 3.
The second point I have is sort of more fundamental. When you use WaveWatch 3 with a highly viscous material, like you have the capacity for generating here, CG is no longer the energy transport velocity. You have to redefine the group velocity when you have a very highly viscous medium. So the WaveWatch 3 code is going to fail in principle if you're using a very viscous material.
That I didn't notice. Actually, when Eric cooperated...
Well, it's no longer the velocity of energy transport because your K is complex, and if the imaginary part is large, then the omega by decay starts to be a little bit tricky. So you have to redefine what the omega by decay actually means.
Yeah.
So it's no longer the group velocity in the sense of it transporting energy.
We're going to get Alexei.
I don't understand why do we need elasticity for this type of file, but as soon as you use elasticity with only non-zero shear modulus and zero compression modulus, so then you will have Poisson ratio -1, and that's very special material, this Poisson ratio equal to -1. So you now will have transition to model of elastic plate with normal parameterization following from classic plate theory. So then, I don't know, but it seems for me that elasticity is not necessary when you consider this broken item.
Yeah, thank you. That's a very good question about Poisson ratio. Actually, when this model developed, they assume it's incompressible. And later they introduced the G and the Shen modulus. Compared with Young's modulus, actually, the fit best is Poisson ratio equal to 0.3. And now we don't know how, I should say, we try to explain why it's conflict between the impression assumption and the good fit of Poisson ratio equal to 0.3, which is compressive material.
It's sorry, it just comes with the time, so just one more question, questions that's up.
I have some doubt about the calibration. So you say that the G could range 10 to 4, and the viscosity is 10 value